Welcome everyone to the machine learning sessions. In this session, we are going to discuss about the partitioning clustering, and the most commonly used partitioning clustering algorithm is the k-means clustering. So let's quickly try to understand the k-means clustering algorithm. K-means is the most used non-hierarchical clustering technique. It is not based on distance. It is based on within cluster variation. In other words, squared distance from the center of the cluster. The algorithm aims at segmenting data such that within cluster variation is reduced. If you recollect, in hierarchical clustering, we had a linkage algorithm which was Ward's method. If you run on a smaller data set a hierarchical clustering with a Ward's linkage, you will get an output which will be very much close to running k-means clustering on the same data set. Because in that case, in hierarchical clustering, it is also using the within cluster variance. Okay. Now let us try to understand the algorithm. I'll try to explain it like a case study. Assume you are doing survey of customers coming to a mall, and you ask various questions to the customers. Why you repeatedly visit the mall? Is it your objective just to basically roam around? Your objective is to see movies in the multiplex? And if you are doing shopping, in that case, whether you are a brand conscious shopper, which means you will buy anything only if it is of a particular brand and of a particular quality, which means you are willing to pay higher prices for the brand, or are you willing to buy anything, any brand, provided the cost is lower? So of the survey, there are many questions. We will focus only on the two questions. One is, are you a brand conscious shopper, and are you a price conscious shopper? The reason I'm taking only two, because pictorially I want to explain the k-means clustering algorithm. N dimensions I cannot project on a screen and explain n dimension. Difficult to visualize. So we are focusing on 2 dimensions. The customers have rated themselves on a scale of 1 to 10. Higher the rating, which means more conscious they are about that aspect. So a person who rates on a price conscious scale 1 to 10, the person rates himself or herself as 10, which means the person is very price conscious, would like to buy things at lower cost. Person who is low price conscious, which means he is not bothered about the price tag. Okay. So the blue dots on the screen, which you can see, are customers. So there is a customer who is somewhere here. The person has rated himself low on brand consciousness and low on the price consciousness, which means this customer is willing to buy any brand, but more the lower cost. Lower the cost is more preferable. Okay. Whereas, sorry, this person is less price conscious. So I interpreted it wrong. This person is low on the brand conscious, and on the price conscious he is rated himself low, which means he is not bothered about price, but at the same time he is not associated with a brand that I am going to buy only a specific brand. At the same time, he is willing to buy any brand provided there is a quality and price tag he will pay. Okay, like a mobile phone buyer. There are people who are Apple loyalist and there are people who are not Apple loyalist. But the people who are not Apple loyalist are not necessarily, they will go with a low end smartphone. In non-Apple brand also they go for high end smartphones. Only thing is they are not too choosy on a brand. They are choosy on the functionalities in the phone. and for those functionalities they will pay money and take any brand. That's okay. I hope this point is very clear. Whereas on this extreme, there are people who are brand conscious as well as price conscious. Chances of someone being too brand conscious and too price conscious are less. If you're too choosy about a brand, then that person cannot be too price conscious. Okay. Or probably taking the same mobile application, mobile buyer example, there may be some people who are very choosy about a brand only. They will choose that brand only, but in that brand they will buy a low end phone. That is also possible, but that exceptions are few. So it is representing only a one smaller dot. If you see in this entire brand consciousness, many dots are on the lower side, right? So this is the data dispersion. When you are doing a clustering, the point one is data is dispersed. Data is heterogeneous. From this heterogeneous data, we are trying to create homogeneous groups. Those homogeneous groups are clusters. Step 1 in a k-means clustering algorithm is you have to decide how many clusters you wish to form. When you call a k-means clustering algorithm, one of the parameters you have to upfront pass is number of clusters you expect to have. This is a very important question. Why? Because when you have data, it's an unsupervised learning. You really don't know whether in your data 3 cluster is a optimal or 4 is a optimal number of cluster. And finding that optimal is a task in itself. We will see it later. But this parameter has to be provided upfront. Somehow for my given data, I have come to know that 3 is the best number of cluster. So I pass to algorithm. I wish to have a cluster. I wish to have 3 clusters. The moment you call the algorithm and pass number of clusters required is 3, automatically 3 centroids randomly will be chosen in the data. In the algorithm, in the backend, 3 centroids will be created. Okay. So these 3 centroids I am representing by C1, C2, C3. Now you compute distance for each object from the cluster centroid. In hierarchical clustering, what was happening? The distance was computed between objects. In a k-means clustering, the distance is computed from cluster centroids. So I will compute this distance for each object with respect to C1. I have not put all the lines. If I put all the lines, the entire screen will be filled with red lines. Likewise, I have to compute distance for cluster 2 and cluster 3. The distance of each object from the centroids. A given object will be assumed. Now let's focus on one of these data point, this one. This record belongs to which cluster centroid? C1, C2 or C3? It will be determined based on this object, how close it is with respect to C1, C2, C3. Whichever is the closest centroid, this object will belong to that cluster. So we will now have to find for each of these objects which centroid is the closest, and we will assign that object to that cluster. So what may happen is you will get something like this. The certain dots which are closer to centroid 1 are marked in the red circle boundary closed area. Certain objects which are closer to centroid 2 are marked with in green closed area. Likewise C3. If you now see these cluster centroids, do you think, just focus on C1, the red boundary area. should the cluster centroid C1 should be exactly where it is if I have to recompute the centroid based upon the objects in the red area? Probably no. Probably if I recompute the centroid, it may so happen the centroid of all objects in C1 may move to some other location. So here I have represented this movement. Similarly, the centroid of C2 may move to some other location. Obviously, there are more dots here. C2 centroid cannot be here. I recompute the centroid. Step 1, the centroids were randomly decided. We started the calculation that way. C3, the centroid will be shifting. So now I get 3 new centroids. What will be the next step? My centroids have moved. The next step is iterate. I got a new set of centroids. I repeat the step 2. Compute distance of each object from the new cluster centroids. I repeat the step 3. Each object will be assigned to the cluster having shortest distance from the cluster centroid. I repeat the step 4. Based on objects assigned to the given cluster, recompute the cluster centroid. How many times do I repeat? Repeat the step 2 to 4 till convergence occur. When is convergence going to occur? Convergence will occur when there is no movement of an object from one cluster to another. Which means after recomputing the centroid, I recalculate the distance, and after recalculating the distance, I see the objects which were assigned to a cluster C1, they continue to remain in C1. They do not move. That's when the convergence will occur. However, it is quite possible you may have a scenario. There is an object in cluster C1. After recomputing the centroid, a particular object becomes closer to cluster C2. So in the next iteration, that object will move out of cluster C1 and get into cluster C2. Now, because one object has moved out of C1, the centroid of C1 has to move. And because a new object has come into cluster C2, the centroid of cluster C2 has to move. Cluster C3 remains as it is. Centroid C1, C2 has moved. You again compute distances. Now, because of the recomputation of distance, it so happens one of the object which was earlier closer to C2, in the recomputation, it now becomes closer to C3. So that object moves out of C2, gets into C3, and because one object has moved out of C2, the centroid of C2 again will change. And because one object has now introduced into C3, C3 will again change. Let's assume C1 is not changed. In next iteration, what happens? One object which was earlier closer to C3, but because of the change in the cluster centroid of C3, that object becomes closer to C1. As a result, this round robin may continue to happen. Because of just one object moving from one cluster centroid to another, the centroid will never become stable. Which means the first criteria, there is no movement of object from one cluster to another, may never occur. Quite possible. If this is the scenario, your convergence will not occur. In that case, you have a second condition for convergence, which the second condition is, or threshold number of iterations have occurred. Because just for one object, round robin is happening, you cannot have these loop going for infinity. So you will put a saying that condition, if 50 iterations has happened, after 50 iterations, whatever is the positions of objects in which cluster, that is considered as final. You may end up having one object wrongly tagged in a wrong cluster. It's okay. We are not bothered about, in all of these exercises, we are not bothered about one object. We are bothered about correctly putting the objects in right cluster for maximum number of objects. We can less likely be 100% accurate. But somewhere we have to say convergence has occurred. So threshold number of iteration is considered as a convergence criteria in that case. If you have understood the logic, all the 5 steps which I have tried to explain in a pictorial way have now been summarized in this slide. K means algorithm summarized. Input required, number of cluster to be formed. Say K. Step 1. You assume K centroids. Step 2. Compute distance of each object from these centroid. Step 3. Assign the objects to cluster with the shortest distance. Step 4. Compute the new centroid, that is the mean of each cluster based on objects assigned to each cluster. The k number of means obtained will become the new centroid for each cluster. Step 5. Repeat steps 2 to 4 till there is convergence, that is, there is no movement of object from one cluster to another or threshold number of iterations have occurred. Now before I move forward, an important question. In the beginning slide, I mentioned K means is not based on distance, it is based on within cluster variation. Explain why it is not based on distance and why it is based on within cluster variation. Those who are watching the video online, pause here, think upon it, and then continue. You will get the answer which I am going to state. Okay, the answer to the question is, in a k-means clustering, you compute distance between object and the centroid. Whereas in a hierarchical clustering, you are computing distance between two objects. And if you recollect the variance formula is x minus x bar the whole square divided by n minus 1, where x bar is the centroid, where x bar is the mean. In this case, centroid is the mean, because as you iterate from one iteration to another iteration, when you go, you recompute the centroid, and centroid is the mean. So what you are doing is, in effect, you are doing x minus x bar. Though we are not completely implementing the variance formula, but in a way, by minimizing the distance from the centroid, you are, in a way, what you are doing is minimizing the variance. That's why k-means clustering is not based on distance, it is based on within cluster variance formulae. Now my next question. Assume you have got 10,000 customers data. In hierarchical clustering, I had already mentioned, in clustering session I have already mentioned, you do not use hierarchical clustering when you have large number of records. You use hierarchical clustering only when you have 100, 150 records. Now let's assume you have got 10,000 observations. How many calculations will happen in the first iteration, assuming you are doing hierarchical clustering? Once again, those who see video online, pause yourself and think of how many calculations will happen in hierarchical clustering if number of objects, number of records are 10,000. In hierarchical clustering, the number of calculations would be, where we have got 10,000 observation, the first record distance will be computed with second, first with third, first with fourth, first with fifth, ... First will get calculated with 10,000. So which means the first record will have to be computed with 9,999 other observations. Then the second record, you will have to compute the distance with third, this second with fourth, second with fifth, second with sixth, and so forth, which means it will be 9,999. Then the third record will have to be computed with the others, which will be 9,997, and so forth, ... till 1. So you get a series of 1 plus 2 plus 3 plus ... till 9,999. If you solve this series, the formula is n multiply n plus 1 divided by 2. That is 9,999 multiply 10,000 divided by 2. You can do the calculation and find out how many calculations will happen in hierarchical clustering. Let's see the calculation in calculator. It would be, sorry, backspace CE. Okay, it would be n plus 1. N is 9,999 multiply n plus 1, that is 10,000, divide by 2. So basically we will end up with 4,99,95,000 calculation if we do hierarchical clustering. And remember, this is just the first iteration. Once you do the first iteration, you will be left with 9,999 clusters, and then you have to do the second iteration calculations and so forth. The other formula to arrive at the same calculation is 10,000 combination 2, 10,000 C2. This is the other approach of doing the calculation. What if you use k-means clustering instead of hierarchical clustering for this? In a k-means clustering, you have to upfront give a number of how many clusters you expect. This is the only challenge in k-means clustering. Before running the algorithm, you have to decide, preempt, and give the number. Let us, for the time being, again take 3 is the number of clusters I want. Number of calculations that it will do is 3 multiply 10,000. Each centroid will have to compute with the 10,000 records. So 3 into 10,000, only 30,000 calculation. Typically a k-means clustering algorithm converges in 20-30 iterations. Assuming it will converge in 20 iterations. In that case, number of calculations for the entire thing would be 30,000 multiplied 20 iterations. So it would be around 6 lakh iterations, 600,000 calculations. In hierarchical, some 5 crore, 4 crore, 99 lakh something, whereas in k-means only 6 lakh. By that time it will converge and give you the outcome. That is the reason k-means is a faster approach when we do clustering. Challenge is you don't know optimal number of clusters. It is a very important element. Why finding optimal number of cluster is very significant in k-means clustering. I will attempt to visually explain this. Hypothetical data, but good for understanding why finding optimal is very significant. Assume your data on a two important dimensions D1 and D2 looks something like this. If I run a k-means clustering and I say I want only 2 clusters, it may so happen that once you run the algorithm, you may get an outcome where you get these 2 clusters, C1 and C2. And you rerun the algorithm on same data next time, provided you are not using seed. You rerun the calculation, you will end up this, and you do profiling. For once you get a different profiling of clusters, second time you get different profile, which means your outcome is not stable. Assume you run this with 3 clusters. There are 4 possible combinations where you will end up. First you may get this, next you may get this, next you may get this, next you may get this, and each time you do profiling, you see I get different profile for my clusters. It will be unstable clusters if you do not choose the correct optimal number of clusters. From this example, I hope you understand the importance to get a stable outcome. Choosing optimal number of clusters is very important. The way we do find out the optimal number of clusters is using a Scree plot of within sum of squares. I have already mentioned in earlier session that the other approach is we use a NV-clust package in R. The NV-clust package in R compares 30 indices, and after comparing 30 indices, it gives you the best optimal number of clusters for your data. We now move into the Jupyter Python notebook where we will run k-means clustering on our retail customer spend data. In that, we will see how to go about using the Scree Plot. I'm switching to Jupyter Notebook, k-means clustering. K-means clustering IPython notebook is available on our LMS, so you can download it from there. Step 1, we'll import the required packages. So I'm importing OS, Pandas, NumPy, Matplotlib. Again, I'm running this Matplotlib inline so that any graph charts that we make will be shown. Changing the working directory and importing the customer spend data.csv. Scaling the data, we have already learned that when we do clustering, we should not use the raw variable. If the raw variables that you have are ordinal on a scale of 1 to 10, when you have variables on a scale of 1 to 10, they don't have unit. In that case, you do not have to do scaling. Scaling is required when there are variables having different units and they have got different ranges. So we will do scaling of the variables. And just to showcase what data we had, I'll quickly run the data, what we are actually scaling. So this is the data. These are 10 records on which we are running the clustering. The same data on which we, in our earlier session, have done hierarchical clustering. So I have scaled that. My objective is find optimal number of clusters. To find optimal number of clusters, I'll use a Scree Plot. Here you can see first what I'm defining is cluster range. What I'm going to do, I'm going to loop through. First I'll create only one cluster. That is, the whole data will become a cluster. Then I'm going to create 2 cluster. Then I'm going to create 3 cluster, 4 cluster, 5 cluster, 6 cluster. How many clusters should I create? Assume I have got 10,000 observations. What is the objective of clustering? Objective of clustering is to create homogeneous group such that variance is reduced. Assume you have got 10,000 customers. How many clusters should you create so that variance goes down to 0? $10,000 clusters. In each cluster, you will have only one observation. That observation will itself be mean. You do x minus x bar. Distance is 0. So variance will be 0. But our objective is not to analyze things at 10,000 level. Our objective is to summarize these 10,000 records at certain level of aggregation so that at a few cluster level we can make decision about the whole data. So the point is very clear. If I have 10,000 clusters, I'll have 0 variance. But if I create all of these clusters data into one population, which means I have only one cluster, which means I will have highest variance. From highest variance to lowest variance I have to move, but I have to move such that I have to find optimal number of cluster, beyond which if I keep increasing the number of cluster, the drop in variance is not significant. So what we are doing is we are trying out building 1 cluster, 2 cluster, 3 cluster, 4 cluster. Each time we will do the cluster, we will see what is the total within sum of square. So here what I'm computing is I'm creating an empty array cluster underscore WSS, and this is where we are going to now loop through. If you can see this one, this line, for num clusters in cluster range. So it is going to loop for first cluster. We call k-means function with one cluster. We are fitting the cluster on the data set, and we are appending the inertia. Inertia column captures the WSS value. We are appending it to our empty cluster area. We keep doing it, and after having done it, we are putting this into a collections. Basically, I'm putting the number of cluster and the corresponding WSS value, and then finally displaying it. So if I run this part of the code, I'll get this table. After having got the table, I'm trying to plot it. This part of the code is for plotting the outcome which we got from above step. When I plot it, we get this kind of a plot. This is called a Scree Plot. Let me try to show it in a slightly better way. What I'm trying to do is I'm trying to squeeze it. What a Scree Plot says that the point where you have an elbow formation, just assume your hand, the point where you have the elbow. So this like your hand, this like a upper arm, and then it starts flattening. The point where there is an elbow formation is the optimal number of clusters, which means beyond that point, the drop in WSS. Here you have seen from 50 I jump down to something 30. From 30 I come down to 20. From 20 I am just moving to 15, which means adding a new cluster is reducing WSS by only 5 points. Where the drop in WSS is not significant as compared to the additional clusters that you are adding, that is the point of elbow formation. So here from this diagram, I'll take 3. Probably this may not be very convincing diagram. Okay, but we know from hierarchical clustering, this is 3. So I'm going to take 3. What is the other approach when you do not get a convincing answer from a Scree plot? If you do not get a convincing answer from a Scree plot, I will fall back on NB clust package which is available in R. I'll switch on to my R, run this code on R with this data set. I'll run NB clust. It will check 30 indices and give me optimal number of clusters. I have done it. That NB clust package also suggests 3 is the optimal number of clusters for our given data set. Once you have found the optimal number of clusters, then the code is very simple. You take the optimal, I call the k-means, n clusters equal to 3, random state equal to 10. Random state is like setting a seed. So we call that, and we get a k cluster object, k-means cluster object. I wish to add the cluster flag in my actual data set. So I call fit predict. In hierarchical clustering, it was cut tree. Here it is fit predict. So I am fitting it on our scale data set to get the labels, and these labels finally I am going to put in the actual data frame. So let us having executed this code, let us see how our actual data frame would look like. This is how our data frame would look like. Here you get the cluster numbers. After putting the cluster labels in your actual data set, next step is profiling. We have already understood what is profiling. Profiling for continuous variable is computing mean. If there are many outliers, then you can rely on median, but typically we use mean. And if there is a categorical variable, profiling means computing proportion, and of the proportion of different categories, you should focus on categories which is having the highest proportion, because that highest proportion category becomes the defining characteristics of that cluster. So we execute this profiling code. Along with this profiling code, I have missed adding another column which is the number of records in each cluster, which you can add as a small code yourself. Having done the profiling, one of the important thing is sometimes what happens is you may want to see the visual depiction of your clusters. So we will do plotting. So this piece of code is what we are going to run. Now, how do you do plotting? How do you do plotting? How many dimensions are there in our data? We have average monthly spend, we have number of visits, apparel items, staple, FNV. On a two-dimensional plane, I cannot show 5 dimensions. To do plotting of many dimensions, what we typically do is we combine these dimensions together using another unsupervised learning algorithm, which is called principal component analysis. So it will combine all of these dimensions and create new dimensions, which are called principal components, such that the initial components will have highest amount of variance in the data. So what we are going to do is we'll run a PCA on the data and take the first two principal components and then plot our data points on the initial two important principal components. So this part of the code is for that. Having done that, we'll now plot these clusters. So I'm saying cluster 0 will be given in red color, cluster 1 will be in green, and cluster 2 will be in a blue color. This is just a color function. And then the plot code, this one. Sorry, this is for labeling, and then this is the display part of the plot code. So let's just quickly run this piece and display the plot. If I run this, you will get this kind of outcome. PC1 and PC2 are principal components. On this you can see A, C, D are here, B, E, G are here, F, H, I, J are on the left bottommost side. These dots are separating from each other. They are not overlapping, which means what clusters I've got are not overlapping to a large extent on each other. If that is the case, which means you have got a good cluster separation. End of day, our objective is a cluster should be homogeneous within and it should be heterogeneous with other. A cluster should be homogeneous within and it should be heterogeneous with other cluster, which means overlap should be minimum. The diagrammatic representation is showing that we are having a separation between our clusters. Diagrammatic depiction is also important. Why it is important? Say you are doing store clustering. You are a marketing manager. You are store manager, not marketing. You are store manager and you are managing 100 stores. And you would like the clustering of these stores to be done. As a person who is managing on a regular basis, you would be knowing which stores are similar to each other. This work has been assigned to some business analyst. The business analyst does the clustering work and he shows the output that, hey, after doing clustering, I feel 5 clusters are there in your stores. And he gives the entire table. Store Thane belong to cluster A. Store Mulund belongs to cluster B. Something. Going through a data which is a tabular format may becomes difficult. If I have a visual depiction where the store names are going to come. As a person managing the stores, the moment I see that certain stores are given a green color and I just see all the names in that, I'll be able to quickly say whether the work done is correct or not, because I will be quickly able to relate this, because based on my domain knowledge and my experience having worked with those stores, I know which stores are similar and which stores are not similar. Only thing what I'm trying to do is get a quantification with respect to actual data, right? And if that quantification is way out of my judgment, my knowledge, in that case I would like to go more deep dive. Why my knowledge is giving me a different perception and why data is giving me a different perception. So many a times visual depiction conveys the message very fast. That's why plotting is important. Obviously, having done the plotting, the last step in clustering is, what is the last step? Naming ceremony. Profiling. Based on profiling, you saw that validation that they have these clusters are same as what we got in a hierarchical clustering. So I have not got into details of the profile of these clusters. It is explained in our previous session. Having done that, the last step in clustering is always a naming ceremony. You don't call a party, but you should give appropriate names. Having done the clustering, what would you do as you get more customers? See, as a business, as a retail business, we have been taking a retail data, right? As a retail data, I'll keep getting new customers. And if I have to keep sending my marketing offers, I have to keep putting new customers in one of these clusters. Where do I put a new customer whose characteristics are average monthly spend is 5,000. Number of visits is 2. The person has bought apparel. FNV is only 2. Staples are 5 items. Where do I put this customer? So the answer may not be self-obvious. If I see 5,000, then this person should be here. But if I see visit, the visits are only 2. So this customer should be here. Apparel. The person has bought apparel. The person should be here. FNV items, only 2, very less. The person should be here. Staples, 5 items. The person should be here. So making a judgment by just seeing the profile may not be easy. How do you now find where this customer should belong? There are 2 possibilities. A clustering is not giving you model. But how can I find distance of this customer from cluster 0, cluster 1, cluster 2? I can. How? See, here what we have done is we have computed the profiling of the clusters based upon their actual spend visit variables. In the clustering process, we did standardization of the variables. Can I have the mean of the standardized variable available for each of these clusters? I can compute mean of the standardized average monthly spend. I can compute mean of the number of visit which is standardized, and so forth. Based on the standardization formula, can I convert these numbers 5,000 to 1 to 5 into standardized conversion? If I store, if I save the actual mean of the population of the sample on which I build the clustering, and if I save the standard deviation of the sample on which I build the clustering, can I compute standardized variable for this new record? I can. I simply have to do x minus x bar divided by sigma for each of the attribute. I get the standardized variable. Now I'll apply new customer standardized variable minus cluster 1 standardized variable, the whole square, summation, square root, that becomes the distance. Likewise, I will compute the distance with the cluster 2. Likewise, I will do the distance with the cluster 3. Whichever distance is the minimum, this new record belongs to that cluster. But in this case, what you will have to do, you will have to store the mean of each attribute and standard deviation of each attribute on the sample on which you build the clustering. And for any new record, you will have to keep doing this calculation, mean standardized variable, and then you have to compute the distance. All of this may make things slightly complicated. The other approach is, once I have done my clustering, I have labeled each record which cluster they belong to. The moment I have labeled each record which cluster they belong to, the cluster column becomes my labeled column, that is the target column. This was an unsupervised problem statement. Clustering was an unsupervised problem statement. It does not give you a model. I make cluster column as my target column, the labeled column. I can now apply a supervised learning algorithm on the same data. Supervised learning algorithm, what it gives you? A model. Once you have a model, any new record you get, you pass it through the model. The model is going to give you a predicted output, and in this case the predicted output will be the cluster in which the new record will belong. So when you do clustering, and if your problem statement requires that on an ongoing basis new record have to be put in one of the clusters, what you should do is the cluster column, you should make it is your target variable. Then you should apply a supervised learning algorithm. You can use a classification tree technique, you can use a linear discriminant analysis technique, or you can use a neural network technique. Any technique, any supervised learning technique which you feel you are skillful at, which you feel is good to be applied on the given data point, apply that. You get a model, and using that model, any new record you get, predict the class, predict the cluster. So this is how we do clustering. With this, we complete k-means clustering. So in our 3 sessions, we have covered the clustering concepts, then we covered hierarchical clustering, and then we have covered k-means clustering. Certain references which I have made use of are given in this slide. The Springer PDF is available online. You can download it. What you have to do is, in Google search, you just type www.springer.com cluster analysis chapter 9. I find this PDF provides very in-depth knowledge on clustering, very good explanation on the concepts of clustering. So it is worth reading this PDF. Download it, take some time out and go through it. It will clarify many other questions which probably I might not have addressed in my sessions. With this, I conclude the clustering session. Thank you. See you in the upcoming machine learning sessions.